Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. If you're joining us live, please remember you can ask questions anytime throughout the webinar. You just have to click the chat button in the top left corner of your Zoom window and then make sure you change the to field so that it includes both panelists and attendees. That's all of our viewers who are with us today. We'd like them to see your question as well. And if you let us know when you are asking that question, please include who's asking the question, if it's a particular student, or perhaps where you're joining us from, school name, teacher name, city name, any or all of that, so that we can give you a shout out when we ask your question. So without further ado, I would love to introduce today's guest. It's Dr. Lydell Wiebe from McMaster University, where he is an assistant professor in the Department of Civil Engineering. Thanks so much for joining us, Dr. Wiebe. I will turn it over to you.
My pleasure. Thank you very much for setting this up, and welcome everyone. It's good to see such great turnout from across the country. I'm originally from Saskatoon, and so I was smiling seeing the people from the prairies. I noticed Campbellford there. My best friend from engineering school grew up in Campbellford, and so it was neat to see that in there as well, and very glad to be here with you today. So let me share my screen and show you a few slides, a little bit of information about what I spend my time thinking about, which is on stable structures. The picture I've shown here, I'm sure many of you know, shows the Toronto skyline. I'm in Hamilton, about an hour's drive away from Toronto. And I was always fascinated by tall and large structures growing up, and ended up going into that field. And so I want to talk to you a little bit about stable structures. Let's see if I can move forward here. There we go. So what I do is in civil engineering, but I thought it would be good to talk about engineering in general. So what you're seeing here is a picture of Hamilton, where I live. There's lots that you can see in this picture that's influenced by civil engineers, which is what I do. So you see some buildings and some bridges. Those are things that are designed by structural engineers, which we'll talk about today. You also see the vehicles moving on the roadway. All of the roads and where they go, those are designed by civil engineers. So much of what we rely on every day for our day-to-day living, particularly in cities, but any sort of gathering of people, is related to what civil engineers do. And so the way I would define engineering is that engineers are people who use math and science to make things that will help people. So we're very interested in learning about math and science, and we're also interested in applying what we know about math and science to make life better for people. And you are surrounded by engineering things everywhere you go. There's civil engineering work. You might not think about it, but when you turn on the tap and you get clean drinking water, civil engineers are the ones who are figuring out how to make sure that the water is clean, how to get it from where it's treated to you, that when you flush the toilet, that it has some place to go and is clean when it goes back into the environment. All of that is civil engineering. If you use an iPad or a smartphone, that's something that involves engineers as well, not as much civil engineers, but other kinds of engineers are involved in using math and science to design all of the devices that you use to make your life better. And so pretty much anything that you can imagine involves engineering in some way, where there are people using math and science to make the world a better place. So how do you become an engineer? I mentioned that growing up, I was interested in buildings and bridges. This was my favorite bridge when I was a kid in Saskatoon. It was called the Victoria Strait Bridge. They've since, they blew it up about a year or two ago to make space for a new one, but it was my favorite when I was a kid. And then I learned that if I wanted to know how to design something like this, I would need to go to school, I'd need to learn about math and science, and I could become an engineer. This is where I am now at McMaster University, and this is where I teach students. So after they go to elementary school and high school, if they have worked hard and done well in their math and science, they can apply to go to university and study engineering. And so I teach people about how to design stable structures, is my part of engineering that I teach about. So how do we make stable structures? I think you already know a fair bit about doing it. If you've ever played with Lego or Mega Blocks like this, I have some here. And I'm sure you've done something like this before. And so you know that if you hold a block in the air, it's not very stable. It drops pretty quickly. So it needs to go on top of something else. It can be stable if it goes like that. Whoops.
I just wanted to offer that if you pause your sharing, then we'll be able to see your demonstration
perfect.
a bit larger.
Excellent.
Wonderful.
Here we go. Let's try this again. So if I try to have a block in the air, it won't pull itself up. It needs something to go on it. In the same way, when we design a building or a bridge, we need to make sure that wherever the load is applied, that it has a way to get down to the ground. Now, if I put it on here like this, and I start pushing on it, I'm sure you've done something like this, it'll fall over. Or even if I hold this, it'll fall apart. So one thing that I can do is if I have two ends to it, and I can put it in here, and now this can carry lots of load, I can push on it really hard and it won't break. If I want something that can push out like that, I can start putting pieces together in a different way. And now I can still push on it, I can apply a lot of load. And so in the same way, just like you've played around with blocks like that and you've figured out what works and what doesn't, engineers have spent time figuring out what works and what doesn't work for designing much larger buildings. Go back to my slides here. So if you're designing, say, a house that you live in, most of those are designed not so much using math and science, but more based on we have built, as humans, we have built many hundreds of thousands, millions of houses over the years. And so we know that one house is kind of like another house. If you build it in pretty much the same way, it will work. And so usually there's not an engineer who's doing detailed calculations to design a house like this. But if you're designing something like, say, the CN Tower, there's only one of them. And you don't get to play with it like you do with your blocks and see if it will fall over. We need to make sure that we know before we build it that it will be safe, that it will be stable. And so that's what we do as engineers. We're dealing with larger structures and we're making sure that we use enough material that it will be strong and stable. And we're also making sure that we don't use too much material or else we're going to run out of blocks and we're not going to be able to build something that's big enough. So the process that we go through involves a few different pieces here. Oops. Here we go. My animation is not working great, but that's okay. So the first piece that we look at is the loads on the structure. So we need to be able to predict something like how much snow will fall on the roof. This is a structure that wasn't designed well for the amount of snow on it, and so the roof actually fell in. That's pretty scary. And so we need to make sure as engineers that something like that doesn't happen. Once we know how much load to expect, that can be snow, that can be people in a building, that can be the wind blowing on a building, it can be something a little bit more extreme like an earthquake. Then we need to figure out how to convert those loads on the structure into forces on the pieces. So for a bridge, like the one that I showed you before, one of the things that I teach students how to do is how to know if a car drives across here, what does that mean for each piece of the bridge? Basically, how much, each piece of Lego, how much force does it need to withstand to hold all of the weight that the entire structure needs to carry? And then we look at the strengths of individual elements. Here I'm going to go back to a video here and show you some of the tests that we've done at my university. So this was something for the class that I was teaching this year. They had to predict how strong this was going to be. It's some pieces of steel that are connected by 2 bolts, and the load that it takes to pull this apart, you can see it's cracked here. We didn't quite pull it all the way apart, but you can see a crack here and that this is opened up. The weight that this can carry is about the weight of an airplane that you would go on if you were flying across the country, a Boeing 737. That's how much load this can carry. So it's a big amount of force, but we know because of the calculations we've done and because we've tested it before, how much this can carry. One of the other things that I asked my students to do is if I take another one here, you can see in this case that the bolts are a little bit closer together than they are here. That changes how much load it can carry, and so we need to know when we're designing it, how much, where we need to put the bolts and how much load something can carry, so that we can design a structure that will be safe and will be able to carry the loads so that you can use it every day to drive across a bridge, to work or live in a building, to go to school. All of that involves structural engineers. And so that is, I think I'm pretty much wrapped up here on what I had planned to talk about. Just giving you an idea of how, as engineers, we're using math and science to make things that will help people and designing structures that should be stable for you and your family to live and work in. So thanks for having me, and I'm looking forward to hearing your questions.
Wonderful. Well, thank you for showing us all those sort of relatable aspects of structures that our students have certainly experienced before. We already have questions lined up, so that's perfect that you are finished the slides. First question is from Ms. Cam's class, wondering what is the maximum distance for a bridge between two buildings with no center support?
Okay. Interesting question. Thanks, Ms. Tam's class, for coming up with that. So for a bridge, you can make bridges very long. There are bridges that go over the water that can be 1 or 2 kilometers long. So think if you're driving on a highway, that's like, it would take more than a minute driving to get all the way across the bridge. That's a long bridge. You could build a bridge between buildings like that, but usually they don't make them quite that long between buildings because usually it's easier to get out of the building and go across. I'm trying to think of the longest bridges that I've seen. They tend to go, say, across the street so that if there are people on one side and they need to get to another side, they don't have to get out of the building. For a longer distance, usually people would not walk anyway, and so you might not use a bridge. There's not really a limit to how far you could go. The thing is, though, the bigger you want to make it, the more material it will take. Just like if I come back to my blocks here. If I want to make a bridge that goes between those two places, I can do it with one little block, and it's pretty easy to do. If I want to cover that kind of distance, then I need more blocks, and it's not as strong. And so I'm actually going to need not just twice as many blocks, but I'll need to put other blocks on top so that it can hold the load. So as we try to deal with longer spans, then we end up using much more material, and so it starts becoming less efficient to do it that way. Thanks for your question.
Great. We have questions pouring in now. Just a quick reminder for those classes who are submitting questions. If you want us to give you a shout out, please do include a little something about where you're joining from, or the city, the school name, something like that in the same text that you give us the question, because there are so many we don't have time to scroll back to those beginning hellos. So our next question is coming from Ms. Payne's class, and Georgia would like to know how a structure that is so tall and skinny, like the CN Tower, stays stable during big storms or heavy winds.
That's a great question, Georgia. Let me I'll show you my picture of the CN Tower so that I can point to that while we talk here. So the CN Tower, if you look at it, you might notice it's shaped kind of like a tree. So a tree tends to be thicker at the bottom and then thinner up at the top. If you look at pretty much any tower, not so much the building towers, but something like this, or the Eiffel Tower you might have heard of, tends to be big at the bottom and thin at the top. Same reason as for a tree, that the loads get bigger the closer you get to the bottom. So that's how something like that can go. Now at the bottom of this, they need to dig down into the ground, and so underneath they go down into the earth so that it can connect to the rock underneath the soil that's there. And they will have designed this using math and science to predict what is the biggest wind that might ever blow on this. In fact, they make a small model of it and put it in a tunnel and blow air at it to feel how much wind goes at it. And they can use that to predict just how strong it needs to be. In fact, for most tall buildings, the hard part, though, is not making it so strong that it won't tip over. It's way stronger than it needs to be for even the strongest wind. The hard part is making it so that at the top, it doesn't bend too much. That less so with a CN Tower, but say with a high-rise building, people will get seasick in the top if it moves too much. And so the really hard part is making sure that people don't even notice that the building is moving. But every building will move in a storm, and we can use math and science to make sure that that the structure will be strong enough that we know that it won't fall over.
Right. And we have a few more questions on the same topic of the CN Tower. Next, we have a question from Ms. Gorell's class, wondering how can you build high structures like the CN Tower, and how do you reach the top?
That's a great question. So the CN Tower is actually kind of a funny one there. I'll go back to it again. So with the CN Tower, it was built in the 1970s, and they built a special machine that could climb up the tower as it went. So all of this is made out of concrete, and concrete is it's kind of a rock that's made by people. So it's wet when it starts, and then it doesn't dry. It has a reaction where it hardens. You can actually make concrete underwater. It'll work just fine. It's not that it dries, but it turns hard. And so they slowly have this machine that climbs up here, and over many, many days, it slowly is adding more concrete on top, and the concrete underneath is hardened. Now, when they got up to the very top here and they needed to put the top pieces on, they're not made out of concrete, they're made out of steel. And they actually used a helicopter to lift up the top piece and set it on top of the CN Tower. because that was the best way to get it all the way up to the top. Sometimes if they're building, say, a high-rise building like this, what they'll do is they'll have a crane that climbs up the building as they build it. And then at the top, they'll bring a smaller crane up in an elevator. And it's a crane that is small enough to fit in the elevator, but big enough to take apart the big crane. And then the little crane will let the big crane down. It'll drop it down the side, and then they can take the little one back down the elevator.
Right. And Ms. Falconer's students are wondering, how long does it take to design a structure like the CN Tower?
It takes a lot of people a long time to design a structure like that. We're talking years of not just one person, but usually a team of people. And what I look at is the structural engineering side, which is how to make sure that it is strong and safe. But there are other people for buildings who are involved in making sure that you have electricity where you need it, and that it's cool in the summer and warm in the winter. All of those things are also go into the design of a building. And then once we know what we want the final building to look like, we also need to figure out how to make every step along the way. And if you think of it like the Lego pieces, we need to make every piece of Lego. And so for a big building, it takes years. It can even take 10 years, longer than some of you have been alive, to design and build a building.
And within that design, Jenny at Eden Rose Public School in Mississauga is wondering, how long do you spend testing models before you build the structure?
So usually we don't test any models of the structure. Usually what we've done is, because we have tested things like this before, we know if I put 2 bolts in a piece of steel like this, we know how strong it will be. And it doesn't matter that this piece of steel is by itself. If you put the same piece of steel in a building somewhere else, it will have exactly the same strength. That's the nice thing about math and science, is we can figure out what will be the same and what changes when you go to a different building. And so in university, I teach students about how to figure out how to turn something that's unusual, like a building or a bridge that there's only one of, how to look at it and figure out each piece. And then the pieces are like things that we've done before. And we've tested pieces like that. We know how they behave. The hard part then is figuring out how to put it all together. Just like when you're building with Lego. Every time you build something, you probably build something a little bit different. But when you've built with Lego enough, you have an idea of what's going to work and what's not going to. So most of the time, we don't actually test the building before we build it. And we do a good job on the calculations so that we know it will be safe.
So it's those calculations then that help you to predict how strong the structure will be, for example, Ms. Hartman's class was wondering how you figure out how many cars a bridge can hold. It's those calculations and what we've built before, that knowledge that you put together.
That's right. So we know there's math and science that we're using to figure out the loads. And what we do is when we design a bridge, for example, or a building, we try to think of any way that we can imagine that it could possibly fall down. And then we can use what we know from math and science to calculate how much load would it take before it falls down in that way. And we know how much load is the most that could be on there. We know how many cars can fit on a bridge. You can't have them 2 or 3 layers high. They can only fit so many on the bridge. And so we know what the most load is that we need to worry about. We check everything we can think of for how it might fall down. And that normally is safe. Every now and then something falls down in a way that wasn't expected. So there's a famous bridge called Galloping Gertie, if you want to look for it on YouTube sometime, where the wind blew the bridge down. And the bridge looked like it would be fine, but it started going like this in the wind. And no one had known to check that before, and so they didn't know that it would fall down. Fortunately, no one was hurt. They could see it being that it was moving too much and no one was on the bridge. And so now we know how to check bridges like that. So every time something falls down, we look at it and we try to learn from it so that we know to check for the next time what might happen.
Right. And switching gears a little bit, we now have a question from Brimwood grade 3 student Jenny, who wants to know, how does an iPhone work as a structure? So we've talked about the big towers and the long bridges. What about little structures like the iPhone case?
Yeah. Hi, Jenny. So most of those would not be designed by civil engineers, but there might be other engineers who look at exactly how thin they can make it, because you don't want it to be too thick in your pocket. You don't want it to be heavier than you need it to be. You want it to be just the right thickness, that it's strong enough, but not too thick. So in a similar kind of way to what we do, they might do some calculations. Usually for something like that, it would be a computer model where they would kind of draw something that looks like it in a computer, and then the computer does the math for you to figure out if you push on your iPhone case here, how much load can it carry. The other thing that they might do with an iPhone is they might not even need to do that kind of thing because it's easy enough to build one. They can build it and test it and see if it works. That's one of the things that's unusual about civil engineering is most of what we design and build is very big. It has to last a long time and you only get to make one of them. And so with an iPhone, you can try lots of things until you find one that works. With a building, we need to make sure that we get it right the first time.
Right. And on that theme of things eventually perhaps breaking down, we have the class at Glen Echo in Hamilton, probably not too far from you, wondering how do you make sure pieces of bridges and buildings don't rust and break?
That's a good question. So there's a few things that we can do. Paint helps to protect from rust. So in fact, the Golden Gate Bridge, some of you might have heard of in San Francisco, that one they paint all of the time. And in fact, they have people whose job is to paint all of the cables that go along. And by the time they get to one end, they go back to the beginning and they start painting again. And that helps to keep it from rusting. So that's one of the things that can be done. Another thing that's done is often around Ontario, where we use lots of road salt, you'll see we tend to use concrete bridges and not steel bridges. Concrete doesn't rust, it's the steel that rusts. And so the concrete helps to protect. There is steel inside of the concrete, and we make sure that the concrete is thick enough that the salt would take a long time to get to the steel. Then the other thing is that rust happens, it happens, but it happens slowly enough that we can usually see it happening. And so we can clean it, we can, with a bridge, usually we'll have a layer on top of the bridge that helps to make sure that the salt and the water, that it runs off to the side and not onto the bridge itself. And so there are a number of things then that can be done to try to keep water and salt away from steel, which corrodes, and also to protect it.
Right. Now, a little bit of a different question now from Mrs. Callahan's class at Marymount in Sudbury, wondering how you build a bridge or perhaps a tunnel under the water. What moves the water so you can build?
Interesting. So there's a few different ways that that can be done. For building something under the water, often what they'll do is it's not just under the water, but it's also under the dirt underneath the water. And so they go deep enough that it's still kind of wet there, but that the water comes in slowly enough that when you make the hole, then you seal the outside of the hole with something that water can't get through, and you go through slowly so that the water doesn't come in. That's one way. Another way of doing it is you can have pieces that you put in and you drop them down. Now, trying to think of exactly how they do that, because the trick is even for something heavy like concrete or steel, when it's full of air, like it needs to be for people to go through it, it wants to float. And so if you try to put it under the water, it's going to try to jump back up. So you have to actually hold it down. So most of the time, I think the main way that they'll do a tunnel would be to try to get deep enough that it's not just in the water, it's actually in the rock underneath, so that when you make that hole, the water's not trying to get in and it makes enough time for them to be able to build it.
Right. And we talked a lot about how long these projects can take, these really big building projects of big bridges or tunnels or tall buildings that they can take years, 10 years. We have a question now from Ms. Falconer's class in Calgary, wondering how large might the team of people work together to design and build a tall structure like the CN Tower?
I'm sorry, the audio cut out there. I didn't hear the question.
Oh. No worries. I will repeat. So we have Ms. Falconer's class in Calgary wondering how large might the team of people be that will work together to design and build a tall structure?
Good question. So it depends on just how big the structure is and different phases of design. So sometimes in the initial design, there might be only a couple of people who are working on it. And then as they're really getting into the details of how to build it, then you might have, say, structural engineers, you might have even 10 people working on it. And then towards the end, you need to make sure that it actually gets built the way you designed. That usually can be, say, 2 or 3 people who are working on that. So that's just the structural engineers. But then you also have people from the construction company who are figuring out how they're going to make the pieces and how they're going to put them together. That can be another few people. Then you have the people who are actually building it. And that can be hundreds of people who are working and operating the cranes and tightening the bolts and all of the things that it takes to build a structure. So in the end, it ends up being hundreds of people who are involved in building a building. Even if structural engineers, it might be 5 or 10 who work on a building.
Right. And we have had a lot of questions come in from different classes and particular students wondering about material choice for buildings. Sophia is wondering what the strongest material used for a building would be. And I know you already talked about some other considerations too, about whether we use steel or concrete based on what might corrode the steel or et cetera. So can you maybe give our students some insight on how those materials are chosen and how we are now perhaps trying to conserve materials as part of that choosing process?
Mm-hmm. So there are 4 main materials that we use for most of what we do in structural engineering. Of those 4, the strongest one is steel, which is something like this that I showed you before. What would come next after steel would be concrete. Concrete is very strong in what we call compression. That's a pushing kind of force. So if I push on something, if I push on it like this, then it's very strong. If I pull on it, it's much, much weaker. So steel is still about 10 times stronger than concrete when you push on it, but when you pull on it, steel is about 100 times stronger than concrete. So usually we put steel inside of the concrete, wherever the concrete is going to feel a pulling force, so that the steel can carry the load. Then we use masonry, like bricks, like the wall beside me here, and there's a pretty good chance that the wall in your room in the school is made out of bricks. That's not as strong as concrete, but it's certainly strong enough for a building the size of a school. And it's really good in fire, and it's pretty easy to build. And then probably the weakest of them, but still very usable, is wood. And most of our houses are made out of wood. Even if your house looks like it's made out of brick, it's probably actually made out of wood with some brick on the outside. So those are our 4 main building materials. And there's a push these days to try to build bigger structures with wood because we can grow more of it. It literally grows on trees. Steel and concrete are a little bit harder to produce, but we can recycle steel. So most of the steel that we build buildings out of used to be part of a car, and then they've melted it down and turned it into steel for a building. There are other materials that are even stronger than any of those. So, for example, there's carbon fiber and titanium, and some of these can be stronger than steel. The problem is that they tend to also be a lot more expensive. And so you might be able to get something a little bit stronger, but you would pay so much more for it that it's actually better to use steel. The last thing that's a challenge with materials as they get stronger is if you have something like a ruler, this can be very strong, but if I push on it, it tends to, this is called buckling, where it would be very strong if I pull on it, but if I push on it, it wants to get out of the way of the load. The stronger it gets, I want to make something smaller, but it's still going to buckle even if it's stronger. And so it seems like steel and concrete tend to be kind of our main materials that we use for big buildings.
Right. And next we have a question about building projects in our classrooms. So the grade 4 class at Ottawa Crescent in Guelph, Ontario are building cranes. Nice. And they're wondering what advice you might have in their planning and building. And we had one other question as well that relates to this on what is the best shape for building something strong. So maybe we could talk about cranes, but in general, as I'm sure there are some other classrooms who are going through building projects, trying to build something strong, what advice would you have as they design those cranes and other things?
All right. So the main thing I would say if you're building something in a class is pay attention to how you connect one piece to the next. If we're designing a real building made out of steel, what I tell my students is the 2 things to worry about are compression and connections. Connections between things are where things tend to fall apart. And that's really true. If you're building something out of popsicle sticks or out of spaghetti or anything like that, usually it's not the material itself that's too weak, it's where you connect them. And so doing that very, very carefully tends to be important for the strength. Then the other thing that to think about in terms of shapes, it depends on what you're trying to do. You might have heard that a triangle is the strongest shape, and that's kind of true. There are some scenarios when a triangle is very strong. Let me see if I can make a triangle like this. So if I want to make a bridge here, If I put a triangle like this, so you can see my triangle, I can push on it and it's pretty strong. But you notice if I push down, it wants to push the two sides apart. So that's why I need the third side of the triangle is to hold them together so that they don't push apart. So if I have something like this that can hold it all together, that triangle is very strong. What you think about with something like a triangle is what parts are you pushing on? This part, when I push down, is feeling a push force. But if I have something here to try to hold it together, it's trying to pull apart. And so it needs to be strong that way. So usually things are strongest if they are, usually they're strongest if you're pulling on them, and then second strongest if you're pushing on them. Sometimes it's nice to be able to design something that bends. Now this is not nearly as strong when I bend it as it is when I pull on it. Right? This could hold, if I was strong enough to hold on to it, I could hang on to this without breaking it. But if I put it like this and I put my head on it, it comes all the way down. It's very flexible when I bend it. So bending tends not to be as strong or as stiff, but sometimes it can work. Now if I turn it this way, now it's actually a lot stronger in this direction. So thinking about where you're feeling pulls and pushes and bending, that can give you some ideas about how to make things as strong as they can be.
So we have had so many specific questions about buildings, and now we had a great general conversation about designing and what things to consider. But I'd like to talk before we end the webinar a bit about maybe why you chose structural engineering, who you work with or collaborate with now in your career, and maybe any advice you might have for students who would like to pursue this area of expertise.
Sure. So how I got into it was when I was even a little kid. I loved looking up at buildings, and my parents tell me that when I was 2 years old, if I was crying in the back seat of the car, they would say that we were crossing a bridge and I would stop crying. Even if I wasn't actually crossing a bridge, because I wasn't big enough to look out the window, that worked to get me to stop crying. That's not true of everyone who I know who's a structural engineer. There are lots of students I teach who they finish high school even, so they're some years older than you. And they think, well, I'm good at math and science. I'm not sure what I want to do with it, but I'd like to help people with math and science, so maybe engineering would be good for me. And then as they learn more about it, they discover that they're really interested in civil engineering. So you don't have to know at the beginning, but for me, it was something that I knew when I was very young. As far as who I work with now, I'm one of the teachers at my school in civil engineering at McMaster University. We have about 20 teachers who teach students about engineering, and we all have different specialties. So I tend to focus on how to design buildings for earthquakes, and I focus on steel design, and then I have other teachers who teach about other things in engineering. And then that's only one kind of engineering. We also have electrical engineering and mechanical engineering and many kinds of engineering, and then also other sorts of things at the university. So there's lots of different teachers, and I talk with people from all over the world about how to design buildings that will be safe. So I will talk with friends in New Zealand, where they had a big earthquake a few years ago, about what they're doing differently now to design better for earthquakes. So it becomes something where we learn from people all over the world. I have students who come from Egypt and from Iran and from China, and I get to know people from all over the world. As far as things to think about and to focus on, what I think some of the advice I would give is to do the best you can in your school. I know it's hard sometimes, and sometimes you have homework you have to do and it doesn't feel like much fun. But those are the things that you need to be able to succeed in some of the other ways. Something else I would say is don't be discouraged. Don't give up if it feels hard or if you feel like you're not as good at it as some of the people around you. Some of the people who I work with who are very, very good engineers and who I respect a lot weren't the best students when they were in elementary school. They had to work hard. They had to learn how to try again, even when something didn't go their way. But eventually they worked hard and they were able to do it. And so I would encourage you to not give up.
Well, thank you so much for that good advice. I was just having a quick look at our chat here, and we've got a few thank yous coming in. The students are saying they learned so much, and thank you for joining us today, Dr. Wiebe.
Thank you very much. It's been my pleasure, and go out and think about the engineering that's all around you. It's been nice to talk to you. Thank you.
And for those of us who might be back for another webinar, you can look at the schedule. We will be posting some more webinars very soon that will happen during Science Odyssey in mid-May, a celebration from NSERC about science and engineering, and we'll be talking a lot about water quality and have some activities there, and I think forensic science is coming up too. So all of that information, as well as information about other programs, including individual video calls with experts like Dr. Wiebe on our VROC program, you can find out more information on pirweb.org. Thanks so much for tuning in today, everyone. I hope you have a wonderful day. Bye-bye.